Hello everyone. Today we are going to discuss about the homogeneous recurrences. In this session we are going to discuss about the generating functions and solving the homogeneous recurrences using generating functions so that using these generating functions we can easily solve the homogeneous recurrences. Now let us see the introduction to recurrences. First we have to know what is a recurrence. A recurrence is a recurrence which is depends upon the previous value. So let us see the definition of the recurrence. A recurrence relation for the sequence an is an equation that expresses an in terms of one or more of the previous terms of the sequence. It means it depends on the previous value for the next term. Let let us see this an is equal to function of a of n minus 1 comma a of n minus 2, like that it depends on the previous value. So if we have to know the value of a of n, first we have to know the value of a of n minus 1 or a of n minus 2 or up to so on a of a naught. Here where f is a given function for the following two illustrative examples of recursive relations. Recurrence refers to the repetition or reappearance of something. We have discussed that recurrence is the repetition or reappearance of a function or anything. It can be reappeared many times or up to the solution is found for the given function. No, it means function. It is a concept commonly observed in mathematics, computer science, and various other fields. Recurrence can be found in patterns, sequence, algorithms, and in everyday life. So if we see, we know that in C program we use recursions. In any language we use recurrences to solve a particular given task. Now let us see some of the examples for the recurrences. So here the first example, an is equal to 4an minus 1 minus 2, which is initial condition is a1 is equal to 2. By using this we can find the values which are n greater than or equal to 2. So let us see how to find this. When it we here given n is greater than or equal to 2, so we use 2 is equal to given equation for an minus 1, n minus here n is equal to 2, so that 2 minus 1 is equal to 1. So a2 is equal to 4 into 4 into 2. So it is equal to 8 in minute. No, here know that a1 value is equal to 2, so that is equal to 8. So by in first example we found that a2 is equal to 8. Similarly in the second, this is a linear first order equation. Let us discuss the orders of the equations later, order of recurrences later. So now coming to the second example, by using these two initial conditions we can solve the given recurrence equation where n is greater than or equal to 3. Similarly, coming to this one, we are by using this equation recurrence equation, and for this initial condition we can solve where n is greater than or equal to 4 conditions. And not only these are the examples, but in generally we use in programming language Fibonacci series. where each previous term is the sum of the its next term is the sum of the previous two terms. Here the first two initial values of Fibonacci series are 0 and 1, where 0 plus 1 is the sum next value of this one. So here 1 plus 1 equal to 2, 2 plus 1 equal to 3, 3 plus 2 equal to 5, 5 plus 3 equal to 8, so up to so on it's continuous. Now coming to Tower of Money, a large problem which can be solved by using the Tower of recursive concept, where the problem is divided into subproblems and we can solve easily. And the last one is merge sort, the sorting algorithm that divides and conquers the every two elements in a sort or array. By using this recursive recursive concept, the merge sort can be solved very easily and in an efficient manner. Coming to types of recurrences, there are three types of recurrences. First one is linear recurrence. Occurs when the next term in a sequence is a linear combination of previous terms. It means its previous term is the sequence which is dependent upon the previous term. And non-linear recurrence involves a non-linear relation between the consecutive terms in a sequence. And the third one is periodic recurrence, describes a pattern that repeats itself after a fixed interval of time or steps. It cannot depends upon the consecutive terms or linear terms. It is mainly concentrating on particular conditions. Up to that condition it goes and then starts from the initial position. It is known as periodic recurrence. So next we are going to discuss about the solving recursion relations. We can solve recursive relations by using iterative method. It means involves calculating each term in a sequence based on the previous terms using a specific formula. It has in iterative method it has a particular formula for a types of uh, recursions. When it comes to characteristic equation, by using this characteristic equation, we can solve the many problems, many recurrence problems, and finds a closed form of a solution. When it comes to generating functions, utilizing generating functions helps convert a recurrence relation into power series for analysis. In generating functions, we can solve the recurrence problems very easily, especially linear homogeneous recurrences we can solve very easily. Now let us see the examples for the solving of recursive relations. So the first given question is 3an plus 1 minus 4a is equal to 0. This is known as homogeneous relation because the equation is equal to 0 and the given conditions are n greater than or equal to 0 and initial condition is a1 is equal to 5. So this given equation is a first order linear homogeneous equation. We can find the order of the equation by subtracting the high subscript value to the lowest subscript value. So here the highest value is n plus 1 and lowest value is n. So that n plus 1 minus n. So n will be get cancelled and 1. So this order is the first order recurrence relation. So this is known as first order homogeneous recurrence relation. So in generally the first order recurrence relations, its general solution is given as an is equal to c to the power of n into a naught. Let us say this is as equation 2 and this equation as equation 1. Uh, we know that a naught is a constant value. Uh, by exception of this one, an is equal to, if an is equal to cn, then we can write an plus 1 equal to c to the power of n plus 1. So let us say it as equation 3. From equation 1, we can write an plus 1 is equal to 4 by 3 into an. And now let us say this as equation 4, so that Cn plus 1 is equal to, and we know that here we got An plus 1 is equal to Cn plus 1, so we can replace An plus 1 by Cn plus 1. So and An is equal to Cn. So by substituting these values, we get Cn plus 1 is equal to Cn. So by here we can write Cn plus 1 is equal to Cn into C, and here C and Cn get be cancelled and constant C value will be appeared as 4 by 3. Now let us now put C in equation 2 in this, so that will get the general solution for the first order recurrence relations. So here an is equal to 4 by 3 to the power of n a naught, and put n is equal to 1 in above, so that will get the value of a naught here, because if there is no a naught value is given, but here we need a naught value, so we have to find the a naught value first. So we have to put here, here given a1 is equal to 5, so we will take n is equal to 1 condition and put n is equal to 1 in the above equation, so that a1 is equal to 4 by 3 to the power of 1. So a1 is equal to 5. By substituting this, we'll get a naught is equal to 15 by 4, and by 15 by 4, that a naught will be substituted in the equation 2. So the general solution is given as an is equal to 4 by 3 to the power of n into 15 by 4. This is about the first order linear homogeneous equation. Now, let us see the second order homogeneous recurrence relation. Here, a given question is an plus 1, an plus an minus 1 minus 6a to the power of n minus 2 is equal to 0, where the condition is n greater than equal to 2, and a naught is equal to 1 and a1 is equal to 8 are the initial conditions. Let us take this as equation 1, and the general form of the homogeneous recurrence relation is given as Cn an plus Cn minus 1 into an minus 1 plus Cn an minus c to the power of n minus 2 into an minus 2. So by comparing 1 and 2 equations, we can uh, take the coefficients as here a coefficients, an coefficients are here it is 1 and Cn. For Cn it is 1, and for Cn to the power of 1, here it is also 1. And coming to Cn to the power of minus 2, here the value is minus 6. So now we have to know the characteristic equation of the second order homogeneous recurrence relation. Let us see that characteristic equation. So here the value will be, it is the second order homogeneous recurrence relation, so that we use the degree of 2 k square. So now Cn into k square plus Cn to the power of minus 1 and k and c to the power of n minus 2, so that we will get the characteristic equation. And substituting the c to the power of 1, Cn minus 1 and Cn to the power of n minus 2 will be substituted in this characteristic equation, so that will get k square plus k minus 6 as equation 4. By solving this equation, we'll get k plus 3 and k minus 2, which are the real and distinct values. For the real and distinct values, we have this general solution like an is equal to a into k1 to the power of n plus b into k to the power of n. So we have to substitute the k1 and k2 values, so that we'll get n is equal to a into 2 to the power of n plus b into minus 3 to the power of n. This will be taken as 5. Now we have to find the values a and b, so that will complete the general solution of the given problem. So we don't know the values a and b, so that initial condition a1 is a naught is equal to minus 1 and a1 is equal to 8. By putting these two values in the equation, firstly a naught is equal to a naught is equal to minus 1, so that put n is equal to 0 in equation 5, so that we'll get a plus b is equal to minus 1, and by putting n is equal to 1, we'll get the 2a minus 3b is equal to 8. So by solving this equation 6 and 7, we'll get a is equal to 1 and b is equal to 2. So that from equation 5, we have to substitute a and b values in this so that we get the general solution of the recurrence relation, which is an is equal to 2 to the power of n minus 2 into minus 3 to the power of n. This is known as the general solution for the second order homogeneous recurrence relation. Let us see the generating functions. So, generating functions are powerful tools in combinatorics and analysis. They provide a way to express a sequence of numbers as formal power series. Generating functions can be used to solve various counting problems. A generating function is a formal power series of the form g of x, where g of x is equal to a naught a1 plus x a plus a2 x square up to so on a3 is a3 x cube a3 x to the power of 3 plus up to so on infinity. The quotients of A represent the terms of the sequence. Generating functions can be used to encode information about a sequence in concise and systematic way. Here, the generating function can also be written as the g of x is equal to summation of, summation symbol n equal to 0 to infinity. So here an into x to the power of n. So when we expand this, we'll get a by using a where a is equal to 1 and expansion of this series. So we'll get 1 plus x plus x square plus so on up to infinity. So the sum of these can be solved by using the formula for this summation is given as 1 a by 1 minus r. Here a is equal to starting value of the series and r is the x minus this coefficient, first coefficient, second coefficient minus its previous coefficient, so that we'll get the r value. And now let us see deeply about the generating functions. Let us see the given sequence of a numbers a naught, a1 up to so on an. They are associated with the generating functions like a of z is equal to a naught a1 plus a1z plus a2 z square plus a3 z cube, so up to so on an z to the power of n and in up to so on, where here z is a variable and a of z is equal to p, where n greater than or equal to 0 and an into z to the power of n, and bz is equal to p, where n greater than or equal to 0 and cz is equal to p, where n is greater than or equal to 0. And we have for the generating functions we have some properties like a of z plus b of z is equal to c of z if and only if for all n greater than or equal to 0 and an plus bn is equal to cn. And associate, it's not an associate, a of z into b of z is equal to c if and only for all n greater than or equal to 0, where the condition is cn is equal to pn of pn and I equal to 0, ai into bn minus I. So by the following these properties, we can solve these recurrences by using the generating functions. Now we will see the solving a homogeneous recurrences using generating functions. Generally, homogeneous recurrences can be solved using generating functions. Generating functions are powerful tool in solving recurrences. Earlier we discussed this. Now in this presentation, we'll explore how to solve homogeneous recurrences using generating functions with examples. Homogeneous recurrences are recurrences where the right hand side is 0. Generally in equation we declare right side is equal to 0. A equation is equal to 0 like f of x equal to 0 is here homogeneous function f of x is equal to 0. Now they are typically represented using linear recursion relation. Our main aim is to find the goal is to find a closed form of expression for the sequence defined by the recurrence. Now we are generating functions for the homogeneous recurrences. By using these three steps, we can generate the functions for the homogeneous recurrences. To solve homogeneous recurrences, we define a generating function for the sequence. The generating function is a power series whose coefficient represents the terms of the sequence. By manipulating the generating functions, we can extract information about the sequence. By generating these generating functions to solve the recurrences, we can easily solve these recurrences. So next we will follow the following steps to solve the homogeneous recurrences by using generating functions. Now let us see the steps. First step is we have to write the generating function for the given sequence. And the second step is use the given relation between and an minus 1 etc. to remove the recurrence from the generating functions and simplify it. Expanding the generating functions obtained 2 in powers of z. Here variable we can take z or x or y any variable. And the fourth step is equate the coefficients of z in two different expressions of the generating functions of the same sequence. Thus obtain the solution of the given recurrence equation. So we can use these four steps to solve the given recurrence problem by using generating function. Now let us see the examples for the generating functions and how to solve these generating functions. Coming to first example, Fibonacci sequence. This can be solved by the above mentioned rules. So the Fibonacci sequence is defined by the recurrence Fn is equal to Fn minus 1 plus Fn minus 2 with initial values F0 and F0 equal to 0 and F1 equal to 1. Let's define the generating function for the Fibonacci sequence as f of x is equal to F0 plus F1x plus F2x square plus up to so on. By manipulating the function f of x, we can solve for the closed form expression of the Fibonacci sequence so that we can solve the Fibonacci recurrence problems by using generating functions. Now let us see the clear information about the generating functions in the next examples. Now let us see the examples for the generating recurrences, solving recurrences using generating functions. As we discussed earlier, the following are the steps to solve the generating functions. Here the given question is an minus 7 e to an minus 1 plus 10 an minus 2 is equal to 0, which is the homogeneous equation, and it is the second order. So we know that highest order minus lowest will give the order of these recurrence relations. So n minus of n minus 2, so that it is equal to 2. It is known as second order homogeneous recurrence relation, and the given condition is for n greater than or equal to 0. So coming to the steps, the first step is let generating function be a of x is equal to summation of n equal to 0 to infinity a n x to the power of n. So that next we have to multiply the in the given each term in the given relation by x power n and sum from 2 to infinity. So as by the second step we will know that we have to multiply each and every term with the x power n and use a summation from n to infinity, so that we'll create a generating function. Here we see after multiplying with x to the power of n and adding summation to each and every term in a given recurrence relation. So we'll get a n x to the power of n minus 7 into summation of n to n is equal to 2 to infinity and so on continues equal to 0. Now we have to replace each infinite sum of an expression from the equivalent expressions. So after solving this equation by after this expansion, we have to start from a2 into x square, then a3 into x cube, a4 into x power 4, and goes on. We'll miss a0 and a1. So coming to this one, a0 minus, for this we'll get expansion like uh, a0 plus a1 a1 x plus a2 x square, a2 x square up to so on, we'll get. So here we'll miss the a1 and a0 and a1 x terms. So and a of x is equal to a0 plus a1 x plus a2 x square plus a3 x cube and up to so on. Here we have a2 x. Here will in the first term we'll start from 2 to a2 x square to infinity, so that we will miss these two. So we have to send these two terms to the left side, so that we'll get a of x minus a0 minus ax. So and similarly for the second term and third term. So we'll get the equation like ax minus a0 minus a1x minus 7x into a of x minus a0 plus 10x square into a of x equal to 0. And now we have to separate a of x terms from the each and every term. So we'll get a of x is equal to 1 minus 7x plus 10x square, which is equal to, we have to send these remaining terms to the right hand side, so that a0 plus a1x plus 7 a0x. So we'll get a of x is equal to a0 plus a1x plus 7 a0 a1x minus 7 a0 x. So 1 minus 7x plus 10x square. By solving this, we'll get the like this. It will comes under the partial fractions. So by solving the partial fractions, we'll get a of x is equal to c1 into 1 minus 2x plus c2 by 1 minus 5x, where c1 and c2 are the constants, and we know that generating function can be written as a of x is equal to c by 1 minus x, so that we can write it as c into uh, some x coefficient is nothing, so it's taken as 1, so 1 power of n. Similarly, we're coming to this equation, a of x is equal to c1 by 1 minus 2x plus c2 by 1 minus 5x. So here will 2 will become, so we can write this equation as c1 into summation of n to infinity, where 2 to the power of n into x to the power of n plus, and this will be taken as c2 into summation of n is equal to 0 to infinity, where 5 will be comes to the numerator as 5 power 1 and x power 1. So express an as the coefficients of x to the power of n in a of x in the summation of the other series. So we can write an is equal to c1 into 2 to the power of n plus a c2 into 5 to the power of n. This is the first example for the summation solving the generating functions in the uh, recurrence relations. Now let us see another example for the solving the recurrence relations using generating functions. Here the given question is an minus 7a to the 7a n minus 1 plus 12a n minus 2 equal to 0, which is the homogeneous second order recurrence relation. So generally we know that a of x is equal to in summation of n equal to 0 to infinity a n x to the power of n, which is known as generating function. And given question let's take a given question as equation 1. So we have to multiply this with summation x power n and uh, some summation terms to the each and every term in the given question, so that we'll get since order is equal to 2, we start the summation from 2 to infinity, so that we'll get the generating functions of the given question. So by multiplying this x power n and summation to the each and every term, we'll get equation as like this. And now we have to expand the each and every term in a uh, question, which are a naught a1 x plus a2 x square up to so on and continues. By solving that, we'll get a of x minus a naught minus a1 x minus 7x 7x into a of x minus a naught plus 12x square into a of x. So we have to take a of x terms into one side and remaining are other into right hand side, so that we'll get a of x of 1 minus 7x plus 12x square is equal to a naught minus 7x a naught plus a1x, so that a of x is equal to a naught plus x into a1 minus 7 a naught by 1 minus 7x plus 12x square. By solving this, we'll get partial fractions like 7 c1 minus 1 minus 3x plus c2 by 1 minus 4x, so that we'll get the final equation as like this. So we know that general solution for this can be written as if 1 by 1 minus ar ax. So we can write this as let's let's take constant as 4. So we can write it as 4 into summation of over summation over n equal to 0 to wait 1 minute, n is equal to 0 to infinity. So now we have to take this remainder a as here. So we will take a to the power of n and x to the power of n for each and every term. So similarly, coming to this, here we will take c1 as it is c1 and summation is n equal to 0 to infinity. So here a is equal to 3, so 3 to the power of n and then x to the power of n. For second term, similarly c2 into n equal to 0 to infinity 4 to the power of n and xn. So finally we get the general solution for the given recurrence relation by using generating functions. A of x is equal to c1 3 to the power of n plus c2 into 4 to the power of n. Now let us see the another example for the recurrence relations by using generating functions when the initial conditions are given. So let's take this equation as equation 1. So let a of x is equal to generating function. Let's take it as a generating functions. Each and every term should be multiplied with each and every term of the given quotient so that we'll get this one summation, and last one summation. So by solving this expansion of this one, we'll get the expansion like a naught ax minus a of x minus a naught, and this one as a of x into x, and the last one is 2 into x plus x square plus up to so on, so that we have to uh, separate the a of x relations and remaining functions into either side, so that we'll get a of x is equal to 1 minus 3x. a of x a of x into 1 minus 3x is equal to 1 plus 2x into up to so on. So we know that in geometric progression 1 plus x square up to so on, we can write it as 1 by 1 minus x. So here it is written as 1 minus x to the power of x minus 1. So it is the inverse. Now we have to solve this, so that we'll get 1 plus x by 1 minus x. By sending 1 minus 3x into right hand side, we'll get 1 plus x by 1 minus x into 1 plus 3x. Here we got again, we'll get again partial fractions, so that a by 1 minus x plus b by 1 minus 3x. By using this, a is equal to 1 minus 1 and b is equal to 2. By solving the partial fractions, we'll get a equal to minus 1 and b equal to 2, and substitute these values in this equation, so that we'll get a naught condition when an is equal to minus 1 plus 2 into t to the power of n, so that here the given condition is a naught is equal to 1. When we substitute a naught value here, let's take it as, let's try this. A naught is equal to minus 1 plus 2 into 3 to the power of 0. So we know that 3 to the power of 0 is equal to 1. So that we'll get minus 1 plus 2. So it's is equal to, it's minus 1 plus 2 is equal to 1. So we have got correct answer, and we have verified that a naught is equal to 1. Now let us see the another example for the when initial conditions are given. So here the given question is an minus 6a into 6a and minus 1 is equal to 0, and initial condition is a not equal to 1. So by using generating functions, we can solve this given equation. Let a of x is equal to summation of n is equal to 0 to infinity and a into an into x to the power of n by generating function 1 multiply each term in 1 by x to the power of n, and summation from 1 to infinity we will get like this in the form of summations. So after expansion of these equations we'll get these equations. So we have to separate here a of x terms one side and remaining all other into RHS side. So we'll get a of x is equal to a naught by 1 minus 6x, so that we know that a naught is equal to 1. So by substituting this value this in this, so we'll get a of x is equal to 1 by 1 minus 6x. So we know that we can write the generating functions like summation in when the generating function occurs in this format, we can write this equation in this format, so that summation of n is equal to infinity to n is equal to 0 to infinity into 6 to the power of n into x to the power of n. Here an is equal to 6 to the power of n, which is required solution. We have got the required solution. Till now we have solved the solutions which first order solutions for which the initial conditions are given in a generating functions. Now let us see the second order homogeneous recurrence relation when the initial conditions are given. Sorry, this is the third order. So let us see that one. Third order homogeneous recurrence relation. So similar to the previous questions, we have to follow the following step. We have to follow the those four steps which are used in the first order and second order. So let a of x is equal to summation of n is equal to 0 to infinity and an is equal to x to the power an into x to the power of n. So multiply each and every term, each term in equation 1 by x to the power of n. So and sum from 3 to infinity, so that it is third order. We have to multiply sum from 3 to infinity, so that we'll get this equation. So now we have to expand each and every term in this equation, so that we'll get the a of x is equal to minus a naught minus a1 into x plus minus, sorry, a of x minus a naught minus a1x minus a2 x square of minus 9x into a of x minus a naught minus a1 into x plus 26x square of a of x minus a naught, and last term is 24x cube into a of x. By now we know that we have to separate a of x terms and remaining other terms. So by separating this, we'll get it as a of x is equal to x plus x whole square by 1 minus 9x plus 26x square minus 24x cube. By solving this, we'll dissolve, uh, what do you say? We'll get this into partial fraction format. So when it's come to partial fractions, we have to separate them as like this. When it is equal to x plus x square by 1 minus 2x into 1 minus 3x into 1 minus 4x. These are linear equations. So a by 1 minus 2x plus 1 by b by 1 minus 3x plus c by 1 minus 4x. Now by solving these partial fractions, we'll get b value as minus 4 and c value as 5 by 2 and a value as 3 by 2. By substituting those values in this equation, we'll get the general solution. And now we have to convert these solutions into general solution, sorry, required solution. So by 3 by 2 is equal to 1 minus 2x. So we know that generally generating functions can be transformed from this form to one. When it is in the form of 1 by 1 minus x, we'll write it as summation of n is equal to 0 to infinity into some constant value to the power of n into x to the power of n. Similarly, here we convert these values into same format like 3 by 2, which is a constant, we cannot be changed. See here. So then summation along with this a value, which is given here as 2 to the power of n and x to the power of n. Similarly, for this term and this term, here it is given. So after substituting these values, we'll get this in the form here. Summation and x to the power of n will be is cancelled, so that we will get an is equal to 3 by 2 into 2 to the power of n minus 4 into 3 to the power of n plus 5 by 2 into 4 to the power of n, so that this is known as the required solution for the given equation. So that we'll use generating functions to solve the recurrence relations, in which are mostly used to solve the homogeneous recurrence relations. Uh, mm, These generating functions can be used in many other solving techniques like counting techniques. This is all about the generating functions. Thank you.